Okay, and I'm minimizing this. Okay. All right, so good evening, everybody. Welcome back. We're going to continue today with sampling variability and central limit theorem, and we're going to talk about probability distributions. So as said, we're moving now deeper into these two topics. We will be also talking about practice labs 3, which is sampling and probability distributions. Then we also will set the stage for probability and probability in diagnostic tests for next week's class. So next week is again in person. I'll return from my travel this weekend. So next week it's going to be in person again. Discussion topic 3 has posted. It's due next week on Wednesday, I believe. Good. Okay. So let's start with topic 3. So sampling, please, if you have troubles hearing me or there are any problems in terms of the screen sharing, just let me know right away. Okay, sampling variability and the central limit theorem. So we briefly started the topic already last time. Today we're gonna go a little bit more in the concept that is relevant in this regard. Well, is anybody else joining? No. I should get notification hopefully. In case you see somebody joining that is not admitted by me right away, please poke me and let me know. Okay, today we're going to talk again about population versus sampling. We kind of illustrate today how these two, how population and sample do relate to each other. This is basically what the central limit theorem entails. We will then also talk about experimental versus observational studies, and then further dig into study design to talk about the differences between prospective and retrospective studies. Also briefly discuss on causality. So essentially, this is important because with retrospective studies, you cannot establish causality versus with prospective studies. In a particular setting, like a randomized setting, you can actually establish with a certain degree of certainty causality because you exclude confounding. So this is consistent with the respective chapters in Open Intro with the book that accompanies the class for you to read up in more detail. Okay, so again, so we talked about it already in brief terms, what population versus sample actually entails. So let's assume you have a population, which is the population of the US, the population of New York City, and you're drawing random small samples. So if you have a mean diastolic blood pressure of 78 millimeter Hg, which is essentially a marker of pressure, and you subset and you create little samples, you essentially will not necessarily get the same mean as you find in the population. So that means you have to distinguish between the population mean mu, which is labeled as a parameter, and a sample mean x bar, which essentially is your sample statistic. So the sample statistic is basically used to then draw inferences, which you basically can then apply to the dynamics you observe or you expect in your population. So in terms of the vocabulary used, you talk about study or sampling units, which is basically an individual element of interest. So this is basically your sample population. You have a target population, that's the ideal population you would like to describe from which the samples are derived. Then you have a study population, that's the population from which you actually can sample. And these systematic differences that are mentioned here, you actually will label selection bias. So that means basically that you have a sample where the mean actually is deviating from the mean that you will know from the population. And the sampling frame is basically a list of all the units in the study population that you actually have at your disposition for sampling. So for the enhance, for example, the sampling frames are little units, which are basically geographical units from which you can sample respective individuals. And the enhance actually has a very sophisticated way to account for the sampling strata and for these sampling frames. And this allows essentially to generalize the enhance dynamics and the enhance analysis to the overall population in the US. So the notation, I mentioned those earlier. So it's important to distinguish between mu and sigma. So the mu is the Greek symbol for U that basically stands for mean in the population, and sigma stands for the standard deviation in the population. Whereas for sample statistics, you basically refer to the mean and the standard deviation as either X bar or M. I've seen M quite frequently, and S, or I will most commonly use SD. When it comes to sampling, the first question is like, how are you gonna sample? So obviously one way to sample is, and which would be somewhat the gold standard of sampling that you would expect or you would hope for when you actually sample from a large population, it would be really random sampling. The problem is random sampling is virtually impossible. But hypothetically, you want to do random sampling. So that means you have an entirely random sample out of your population. This is, it can be done with this R function here that we will do later with the houses in Iowa. But hypothetically, this remains somewhat a hypothetical approach because it will be very difficult, particularly when it comes to the recruitment of studies, which requires voluntary consent of the participant. It will be impossible to basically do random sampling. And that will almost always create some form of bias. Then you can also approach it with systematic sampling. So there would be, as listed here, it could basically be that you give each individual out of a group of 30 individuals, you give them a number from 1 to 30, and then you move on. You start with 2, you add 3, and you take 5, then you add 3, you take 8, and you take all these individuals that have the number with these increments of 3. It is somewhat comparable to systematic, simple random sampling, but it is more systematic in nature. What is more commonly done is stratified sampling, which essentially is a stratification of your population, where you sample from respective strata in your population. That means you have strata of interest from which you want a certain representation from. That means you stratify in strata of biological sex, in strata of, I don't know, race, ethnicity, diabetic status, congestive heart failure, comorbidities of all kinds. You can go as far that you hypothetically you stratify as per the magnitude of a parameter of interest, and you only sample from, let's say, patients that have a blood pressure exceeding a certain threshold. So these strata are actually quite often found. The resulting almost downside is that it becomes less generalizable, and the variances are, as a consequence of that, they will be smaller than you would see in simple random sampling. What is also commonly seen is cluster sampling, and clusters are basically by definition clusters of all sorts. So that can be geographical cluster, that can be clusters in terms of structural units. In my world, for example, we use a lot of clusters when it comes to dialysis clinics, for example. So you can either have several clinics within a certain geographical region, or certain clinics with a certain characteristic, or you can have the clinic per se representing the cluster. So the sample variance then becomes larger because of the clusters, they're smaller, and you have essentially then more variability just caused by these geographical constraints. So here, for example, you have here listed counties. So those are potential strata. So it's really everything that kind of defines certain boundaries of your sample framing unit. The problem you have, and this is what I mentioned before, so in most cases, you want samples that are generalizable, that are randomly sampled from a population. However, the problem here really is that in most cases, you will not be able to do random sampling. Reason for that is that, particularly for prospective studies and prospective randomized studies, in its most what should I say, most advanced format, will require that you have participants that are willing to actually participate in your study. So for that reason, you are restrained to volunteers, or you are constrained as per the eligibility criteria. You're restrained to patients at a cancer clinic because they're accessible to you, because you work in the same hospital or you work in the same clinic, or they are patients of interest for you. However, these are all to some extent convenient samples. That means they're lacking generalizability. So they are convenient to sample, but essentially they come at the price of generalizability, and therefore you have some form of bias in your demographics and in the distribution of your study population. The problem is that you don't really know the probability of selection. You don't really know how large that bias will be. So there are some analytic ways how you can quantify the bias and how you hypothetically can account for it to some extent. But in essence, the only thing that really helps with selection bias is by replicating your study. So selection bias is the resultant, and the selection bias will then essentially lead to a lack of generalizability. So these are really the most commonly stated disadvantages of sampling and poor sampling strategies. Also of note, and I mentioned this, I believe, in last class, when it comes to medication that is being prescribed to, and there are some studies that basically claim this quite strongly, that most randomized controlled trials that have studied antihypertensive medication or whatever medication you could think of are essentially not really studied, at least not in the prospective parts of their study. They're not generalizable to the population they're actually being used in. So this is actually one of the downsides of these things. So you basically assume that these will be equally effective in the population they're essentially then being used in. So this is just the specific case of sampling strategies. So when it comes to geographic sampling, and just that you can kind of illustrate and kind of think of this in actual depicted terms. So with simple random sampling, you would actually sample from strata within this overall depicted grid here on the left. So if you randomly sample, you get different probabilities of actually selecting individuals, because if this yellow signs basically indicate here the population density, you would sample from very population scarce areas, thereby you were restricted in your actual demographics, and you will get a biased sample on your simple random sampling. So it's hard to follow simple random sampling in practical terms when it really comes to geographical distribution of features. Systematic sample would then essentially be a very systematic sample across the geographic regions. Stratified samples would basically use then geographic demarcations as boundaries, as natural boundaries, which again will possibly introduce biases. or you can follow a non-probability sampling, which is a form of a convenience sample that basically covers the areas of most population density. So this is in geographic sampling. This is a very peculiar case, and this is what I mentioned before with the NHANES. So NHANES basically created sample framing units, which basically got then a weight according to the population density and the probability of a certain feature being present in the respective strata unit. So, experimental and observational studies. So, are there any questions on sampling so far? I think it's quite intuitive. It's basically quite something that is quite self-explaining. Well, I just want to make sure that there's no internet problem or anything. It tells me at that very moment that the internet connection is unstable. So can you hear me well? Yeah, perfect. Thank you. Thanks for the thumbs up. All right, good. Okay, so we have experimental and observational studies. So I think to some extent it's quite intuitive what that implies, but basically with experimental studies, you always kind of assume that there's an intervention. So that intervention is in a perfect case scenario, and this is considered the highest level of scientific evidence, is being administered in what is called a randomized controlled trial. What it basically entails is that you have experimental groups, or one experimental group at least, and you have a control group, so randomized controlled. Analytically, that basically means that you will follow patients into their progression into the study, and the control group, you are not making subject of the intervention, and then you compare the dissociation of both groups in terms of a parameter of interest or variable of interest. So you would randomize then in treatment and control groups, and you can, and this is where the real benefit is of a randomized controlled trial. So what is most feared when you compare two groups is what is called confounding. Confounding means that you have a preponderance of a certain characteristic in one of the groups. Let's think of, for example, you study an antihypertensive medication. You give one group an antihypertensive medication, and the other group you give, I don't know, just a sugar cube. So you don't give them a real drug. You don't give them a real medication. So hypothetically, you should see a difference between these two groups at the end of an observation period of, let's say, 6 months. The problem is, if you have now in one group a larger number of patients that do have high blood pressure, but in the other group you don't, you will miss to see any difference of that intervention. And therefore, only randomization in the respective arm will allow to minimize the effect of confounding, which is basically a preponderance of one characteristic in one group over the other. So you want an equal distribution of both, of all characteristics between both groups. This is in trial design words, this is called the so-called equipoise. And you will hear that in the clinical trials class for sure. As a consequence of that, experimental studies that are randomized are essentially the only way to prove causality. Why? Exactly because of that. Because you will not be able to prove that there is actually an association that is not just simply an association, but is actually really a causal relationship to essentially prove that with any other studies. So when you have a retrospective study, for example, it's virtually impossible to prove causality. Although, and this is what I shared on the module, there are some quotations from Bradford Hill, which is in epidemiology, it's nowadays still taught. These are ways how you can suggest causality. Again, it's suggesting, it's not proving causality, but you can suggest causality based on 9 different points that Bradford Hill, I think it was a CDC director, I'm not sure when, but definitely in the last century, I think in the 70s. And he basically made those 9 points that basically will suggest causality in epidemiological studies. So you have the strength of associations, you have a consistency of finding certain results, you have a specificity, you have temporality, which means one event is before the other. You have a dose response, which is also important in this context, plausibility, which is a biological dependency, biologically plausible pathway. You have coherence, so it does not conflict with a generally well-known fact. You have experimental or non-experimental evidence that does also support this finding, and you have analogy. So, analogy would be that a different drug has the very same effect. So these are the 9 points which are to be kept in mind, but they do not prove causality. So this really can only be done in adequately powered studies, so which is a precondition to establish causality. Okay, any questions on causality? Any questions on study design at this point? No? Okay. I miss being in the classroom. It's just much more interactive in the classroom. Okay, good. Okay, so let's carry on. So observational studies are basically those studies where you don't have this intervention. So observational studies are those studies where you have either you follow just a cohort of people, or you follow several cohorts of people prospectively, so that would be prospective observational, or you look for cross-sectional data, where you have a random sample, like the enhanced data that you have at your disposition. This is typically observational cross-sectional data. Or you go back and you analyze data that was collected for a different purpose. So in my case, for example, we do a lot of retrospective epidemiological studies where we basically collect data for clinical decision-making and for clinical observance. And we're going back at this data, we're extracting them from our database, and we do predictive analytics on this data to basically find out what actually predicted their risk beforehand, and then bring this to on the next level and use this for clinical decision making or for the design of future studies. So this is the retrospective. So basically the subjects are recruited based on health status. So this is, in my case, it would be dialysis patients. Their data is collected for the sole purpose that they are dialysis patients. They're receiving treatment, and we're collecting their data, and we're using their data for decision making. Prospective is where cohort is followed through time. So the nurse's health study is one of these examples, and observational studies cannot prove causality as established. They can suggest causality with more emphasis when these 9 criteria from Bradford Hill are met, but they cannot prove causality. So experimental versus observational studies. So if you want to establish whether smoking causes lung cancer, so it's a very extreme example, but it basically illustrates the need for retrospective studies and to not just a priori study everybody in a randomized setting, despite the costs and the efforts that are needed. It's also that in many cases, it's just unethical and absolutely not feasible to basically conduct prospective experimental research. So if you experimentally would like to prove that, that smoking causes lung cancer, you would need to randomly assign never smokers and smokers to either smoking or non-smoking groups, and then follow them for years to see if they develop lung cancer. So obviously this is if you would get this to an ethic board or to an institutional review board, it's like they wouldn't even look at any further explanation of your study. So obviously it would be unethically, it's not feasible, and it's just not possible to conduct this research. So you're really restrained to some extent to observational data at this point. So only in such cases you can actually, with meeting these 9 points often and impressively enough and making the case strongly enough, you can sufficiently establish a causality that kind of can be assumed and can allow for future recommendations. So with smoking, for example, this was one of the so there were long discussions. I don't know who of you is aware of these discussions, but there were long discussions basically by research from the tobacco industry whether smoking actually does cause lung cancer. So, but nowadays it's generally accepted that lung cancer definitely is at higher risk in smokers. Okay. So observational approaches here with smoking and lung cancer would be just a simple survey. So this obviously comes with a big caveat, because you only get a cross section. So if you have a very large group and you ask lung cancer patients how much they have smoked in the history, then you can kind of make an assumption about whether there's an association. This would be in a cross-sectional setting. Often this would be labeled as a case control study. So it depends then on the study design, but you could hypothetically, you could establish, because you could find evidence for a possible causality in that fashion. Retrospective would be you recruit 50 cases, and then you follow them, and you basically, at one point, you basically retrospectively review their smoking status, and you follow them up in what respect this associates with lung cancer. Prospective would be that you quote unquote allocate smokers and non-smokers into groups, and you follow them over a long period of time, and then you count the rate of lung cancer incidence. But it's not randomized. So this would be labeled a cohort study. A little background on the terminology used here. A cohort study is basically a cohort derives from Rome. It's from ancient Rome, a military term. So a cohort was a group of 500 soldiers that marched into one direction towards the enemy. And so it's used now in trial design terms and in study design terms, because you have a group, a cohort of individuals, of study participants that are marching in one direction along a timeline, and then you observe what happens to them over time. But this is a cohort study. A cohort study that is randomized would be a randomized controlled trial or a randomized study. So, but back to population versus sample. So are there any questions on study design? If not, then we can carry on to population versus sample. So here, basically, that's a distribution of running time in the 2009 DC Cherry Blossom Run. So this is a 10-mile run. So we have 16,924 participants, and they all ran this run. So now when you look at all participants, this is obviously a population mean, right? So if we're sampling from this 16,000 or 17,000 runners, 100 runners, this becomes a sample then. So what we see here is that the sample mean, which you would assume somewhere here around the mode, is definitely not the same as you would expect here. Well, it's somewhat comparable, but it's not entirely the same as you would assume from your population, which feeds into what I said before. So you have, you're taking a sample, you calculate the sample statistic, which is your mean of your sample. If you do this a second time, you get now a distribution of means. And this is what we discussed last time. So this distribution of means is basically the distribution of the sampling distribution. So this distribution of the sampling distribution. So you get a sampling distribution which will be skinnier than the actual population distribution, because the population distributions are individual scores, individual serum cholesterol levels, like in this example here, which have much more extreme values, and this will follow a certain standard deviation, a certain variability around this mean, whereas the mean of the sampling distribution, so that would be the mean of all your mean sample, of all your sample means. The mean of means is likely to be very, very close to your population mean. However, the standard deviation of your sampling distribution is basically not consistent with the standard deviation of your population. And this is what we discussed last time as the standard error of the mean. So we have now each sample mean is just one data point on the sampling distribution. So if you have 100 runners out of these 17,000 runners, you get basically one entry point for your sampling distribution. If you get now, let's say 100 samples of 100 runners, and you take out 100 runners and you drop them back, you drop those 100 runners back in your population, but you only keep that mean, this will build up the sampling distribution. And why is that important? Because it's important because using this principle and using the central limit theorem will basically allow for you to transform what you know from the population into probabilities from your sample distribution. And this will allow for you to make inferences of your data. So the central limit theorem basically relates the sampling distribution of means, so it's the distribution of means, to the population distribution. And what you essentially will have as the first assumption is that you assume that the population mean and the sampling distribution mean X bar, which in a practical case is the mean of your one sample. So you draw one sample and you analyze that sample under the assumption that it's generalizable to your population and that the mean of your sample is actually identical to your population mean. And then you carry on and you use that sample mean and the variability that you will then derive from either the population mean if it's given, or from the variability in your sample to basically draw inferences using the principles of the central limit theorem. So first, you assume that the mean of the population and the mean of what you assume to be your sampling distribution are identical. So this would be this depiction here. Secondly, you're trying to estimate this variability in your sampling distribution by relating the standard deviation of the population to the so-called standard error of the mean. And the standard error of the mean is the variability of your sampling distribution. So in a set test, which is the simplest test that we will touch on today, in the set test, you assume that you have, and you're not only assuming, you have the standard deviation of the population given. So that's one of the preconditions for a set test. So this standard deviation, you then divide by the square root of the n, which is the sample size of your sample. And this sample size is basically allowing you then to estimate your standard error of the mean. But this is the variability here that is depicted here in blue. Whereas the standard deviation is the sigma that is shown here in red. What this also entails is that if you have large sample sizes, the shape of your sampling distribution becomes normal. That means even though the population may not be normal, and sometimes this doesn't present as normal as you would wish it to be, if you assume the sampling distribution, the means that you draw. So you basically assume this is the result, this is the mean of means of repeatedly drawn samples. This sampling distribution will follow a normal distribution shape. So this is again the same depiction. So again, so you're drawing a random sample. You have a mean mu and the standard deviation sigma that you then use for inferences of your sample. The standard error tells us how much variability to expect. So this is basically how we will get to inferences, how we actually make decisions based on our sample statistic. So if you have larger sample sizes, so there are a couple of things that are coming there in your favor. If the sample size is at least 30, you're always getting a way to assume this is a normal distribution, although it may not be a normal distribution. But sample size kind of offsets the downside of this not being a normal distribution. For example, you can, with a sample size greater than 30, you do not need to use a t-distribution, which we're going to discuss next class, no, in 2 classes. So basically, so the larger sample size, the more it takes a bell shape, and the more likely it is a normal distribution. So when you have proportions, so now it gets a little trickier. So now we're moving on to basically deal with proportions. So when you look at a population and you have a certain fraction of diabetics and non-diabetics in your population. Let's say you have 10% diabetics. You have with each time you draw an individual, you have a certain probability that you will draw a diabetic individual. That means with 10% in a sample of 100 people, so let's say you have a population of 1 million people, how much is in New York, like 7 million people, you have 10%, you have 700,000 diabetics. You draw a diabetic with a probability that is basically corresponding with the proportion of diabetics in your population. If you draw a sample of 100, you get 10%. That means 10 individuals do have diabetic. That is not necessarily the case. It can be with one sample, it can be 7, with one sample, it can be 12, with some sample, it can be 9. So this could vary, that number of individuals in your sample population. So this is here depicted with a certain proportion in your sample. So this sample actually would translate then an actual count of individuals with a certain characteristics. So if you repeat this now, let's say you draw 100 samples of each 100 people, you get different estimates for that proportion in your samples. So these different estimates will basically also distribute in a normal distribution, in the shape of a normal distribution, whereas the mean of means with this mode of this normal distribution in a perfect case scenario and consistent with the central limit theorem represents that actual proportion that you would assume to be present in your population. And you can actually approximate a normal distribution, and you can use the so-called normal approximation to quantify the standard error of the mean of your proportion, of your estimated proportion based on your sample. So, but we will do this in the next topic, actually, in more detail. The same you can do with the central limit theorem when you do inference with the so-called z-test. So if your sample size is 30 and you do have the standard deviation of your population given, you can quantify now. So this denominator here is essentially the standard error of the mean. So you have here the standard deviation of your population divided by the square root of the sample size. So this gives you the standard error of the mean. X bar minus mu is essentially the difference between your sample mean and your population mean. So to bring this in other words, what you're trying to do with a z-test is to compare your sample mean to the population mean and quantify, knowing the principles of the central limit theorem, quantify the probability of this sample mean being consistent with the population mean. And this is now where we actually get to z-score testing. And this is where we talked last time about the z-score table. You remember that last time we talked about So you also have on today's class, you have a file called z-score tables. And this file essentially quantifies here the so-called z-scores. So we talked about this last time. It's quantifying the fraction of a population that is corresponding with the distance from the mean expressed in the number of standard deviations. If you are now using the central limit theorem, you are not quantifying this as a fraction of a population, so it transforms here essentially in probabilities. So you have the normal distribution and you use the standard error of the mean to quantify the probability of this population mean being inside of the bounds of this standard error of the mean. So you're standardizing your sampling distribution according to the standard error of the mean. So when you think of this graph here, right, where is it? When you think of this graph here, so you have here sampling distribution. You know that the variability around the sampling distribution is quantified as the standard error of the mean. So this is the spread of your sampling distribution. You standardize this using the standard error of the mean, and then you're quantifying the probability of the population mean being located close enough to the mean for this being essentially being considered coming from the same distribution and not being a significantly different sample from your population mean and your population distribution. So, and this is done, as we discussed last time, with the z-scores and the standard error of the mean. And if this z-score is basically larger than 1.96, and the way you're reading this table is basically you're reading from the first decimal, you're reading along the rows here, and the second decimal you're reading along the columns here. If it is exceeding your 1.96, so basically it measures outside from the mean. That means -1 is one mean below the mean, +1 is one standard deviation above the mean, and then it continues up until 1.96. So if it exceeds your set of 1.96, you're basically exceeding 1.96, and your probability gets smaller than the 2.5% that you will need for a two-sided 5% threshold of this being actually from the same distribution. And if this is exceeded and this probability of this coming from the same population, you are rejecting your null hypothesis and you assume this to be significantly different from your population mean. We're going to do an example later on, but this is the principle how you essentially look at this quantification. So you actually, okay. So we have here that difference between the sample mean and the population mean, and you're dividing it by your standard error of the mean, and thereby you're quantifying these differences between the sample and the population mean. And if this quantification, if this difference and this standardization basically exceeds 1.96 as a z-score, you will assume this to be significantly different. This is also then translated into confidence intervals, which we will discuss in a bit more detail in a later class, where the confidence interval basically is an interval which contains exactly this 95% confidence within which you're confident that your population mean is basically contained in. And this is quantified using these boundaries of a z-score. So when you calculate the z-score by quantifying the difference in the numerator, dividing it by the standard error of the mean in the denominator, and you get then as a resultant, you get a z-score. So this is hypothesis testing. The other way around you can do is essentially to also, if you know a set that you're interested in, so 1.96 corresponds with 2.5% probability. Since it's symmetric, that same accounts for positive 1.96. So if you're quantifying this now as 5%, the leftover of 100% probability, you have 5% on the outer ends, on the tails. The 95% inside do have the boundaries of 1.96 on both ends. And you basically can now replace the set with 1.96, and you can basically now rearrange, you multiply it with the standard error of the mean that you have given. So you get 1.96 multiplied by the standard error of the mean, plus your mean, that gets you exactly, plus and minus that mean, that gets you exactly those positive and negative bounds of your 95% confidence interval. But we'll discuss this in more detail. So, but why is this important? This is important because this central limit theorem, where you relate the population distribution to the sample distribution, is basically the basis for all analytic, parametric, and parametric tests that we will be doing this rather short and comprehensive semester. It forms the basis of ANOVA, which is something that you will be hearing about in one of the later classes. And of course, also the confidence intervals, which are important for all the hypothesis tests that we will be doing, as well as for regression analysis that we will be doing later on. Okay, so essentially, so large enough really, tell us the sampling distribution for large enough n. Don't know the population distribution. So there are ways that you can estimate the standard deviation of the population if you don't have it given. So you will know the population standard deviation because you will need that to estimate the distribution of your sampling distribution. You will need to know that to quantify your standard error of the mean and your variability around the mean of means, that's sampling mean. If you don't have this population standard deviation given, you can estimate it based on the standard deviation in your sample. So that's one way. So there's an arithmetic manipulation involved, which we will discuss when we talk about t-distribution. And this can be done with sample sizes of up to 30. With this little manipulation, everything greater than 30, you can basically use the regular approach. We will talk about this in more detail. But basically, the size of the population does not affect representation. Yes, okay, this too much detail. Okay, so we talked about sampling distribution and population distribution. We talked about how they relate with the central limit theorem, and we briefly talked about study design. So now we would go further into probability distributions and see how that basically relates to what we just discussed. Any questions on any of this so far? I know it's a little bit much material today, but it's a little bit of a time is of essence. Okay, so if no questions, then let's carry on with probability distributions. I will go a little bit faster through this because that's a lot of arithmetic theory. We do some simple examples, but I will not spend overly much time on the details. So basically, probability, and we will talk about this more next class. So probabilities are basically quantifying the probability of an event occurring versus not occurring. So you have a probability of 100 that an event will occur or an event will not occur. So if they are mutually exclusive, so either you have cancer or you don't have cancer, this will add up to 100. So these are notation details that are not relevant in this current aspect, but basically what you will need to understand is that there are independent events and then there are joint events. So I spare you the notation details, but basically you have a union, which is A or B, then you have intersections, which is A and B, and then you have A complement, which is not A. What will become important next class is conditional probability, where you assume the probability of an event A needs to occur that an event B will actually occur. So you have joint probabilities and marginal probabilities, but we will only discuss conditional probabilities next time, speaking about Bayes' theorem. So definitions, we talked about definitions last time. We know about definitions. We know blood groups, for example, here are categorical variables that basically are nominal in nature. Then we have here random variables. So this is basically a discrete quantitative. So we have here the visit per se, 0, 1, 2, 3, 4, that could be treated, although it looks like an ordinal variable and could be treated as such, is essentially it quantifies discrete quantitative because it basically then gives you an idea about how many women did actually have 0, 1, 2, or 3 visits. The distribution of BMI in a population, that's a typically continuous variable. Basically, it is continuous because the individual data point can take on any random value, any positive value notably. So that would, if you would want to classify it even a little bit in more detail, you would call it a ratio variable because it basically has a meaning for 0 and it can't be less than a 0. So it can't be negative. Whereas interval data would basically also take on negative values. And now we're coming to what actually is relevant. So when talking about probability distributions, so you get with these frequency polygons, you have here the entire population under this frequency polygon. If you denote a certain interval in this frequency polygon, this indicates a certain fraction of your population, but then also relates into a certain probability of you drawing out of a population an individual that has a value between this and the upper bound. When it comes to sampling distributions, as we discussed earlier, this probability basically indicates the relationship between the sample mean and the population mean. So this is true for essentially all distributions. You can always quantify, if you know this arithmetic function that denotes this frequency polygon, you can actually always quantify the area that quantifies a certain percent or a certain probability in your data set. Yeah, and with confidence intervals, we will be quantifying these intervals. Each interval has a cumulative probability between 0 and 1. So min and max would basically have 100% included. So you have a normal distribution and a binomial distribution. For a normal distribution, you essentially demark it with a bell-shaped curve. For binary outcome, it's basically the probability of an event occurring or not. So you assume again that there are random samples of yes versus no, which are these mutually exclusive events. And they will end up in their sample. It's either yes or it's no. So this is why it's called a binomial distribution. And you would have the principle of normal approximation to basically assume that if you draw random samples and you have 100 samples where you sample this yes and no condition, you get different estimates for each of your samples. And these different estimates will again follow a normal distribution. So this is the normal approximation where basically binomial distribution is then be quantified by the principles of a normal distribution. So we've learned about that. This is the empirical rule that we have discussed last time. We have talked about population. So you have a mean, which is mu here. You have z equals -1, which is the mu minus 1 sigma. You have z plus 1, which is mu plus sigma. Within these two standard deviations, you basically have 68% of your population. If you subtract 2 sigmas from your mu and you add 2 sigmas to your mu, you have 4 standard deviations now. And this basically contains then 95% of your population. If you do the same exercise with 3 standard deviations and you characterize it with 6 standard deviations in total, you quantify 99.7% of your population. So, and this can obviously also be calculated. So if you know from a population, you know the mu and you know the sigma, you can indicate and calculate these actual values. And this is where I said, this is really important to keep in mind when you read the scientific article. You can basically look at your at that article at hand, and you can quantify yourself. How does this data distribute and how does this sample distribute? You can use simple arithmetic rules to quantify your normal distribution. So essentially, if you assume this entire distribution to cover 100%, you can basically now calculate 50% will be here. You know that 68% is between -1 and +1, and 50 plus 34, which is half of 68. 50 plus 34 is 84. And this 50 minus 34 will be 16. So you can quantify and characterize your entire normal distribution following these simple empirical rules. You can also quantify it with actually functions. So there are functions for that basically characterize the normal distribution as a mathematical function. And you can then use these standardizations to essentially calculate your actual z-score and then use this using the norm dist function in Excel or other functions in R that we will see later to quantify the actual percentage that is found below a certain point or above a certain point or between 2 points. So there are ways to actually do that. So we talked about standardization. So the calculation of the set we have discussed already. So it's basically x minus mu. So this is the individual data point minus your mu divided by sigma, your standard deviation. And this is the same formula that you basically see before, when we talked about Z equals X bar, that's when we talk about sampling distributions. So this is where that X transforms into X bar, because X bar is there only one data point in your sampling distribution. So this is when X bar is basically referenced and compared to your population mean and then divided by the standard error of the mean. Whereas when it comes to individual scores in a population, you have an X, which is a random entry, minus the mu divided by the sigma. That basically gives you an actual set score of a population where you standardize the population. This is basically just how you have to look at this. So if you have here population distribution, a normal distribution of a population, and you're standardizing it into set scores, you get the same population, but you just get them standardized into set scores. And you can express every value that each of your constituents in your population has into set scores. Vice versa, you can identify individual values by knowing individual set scores, and you can utilize those to demarcate certain fractions of the population. So let's say you want only 2.5% of your population as being used in inferences when we talk about sampling distributions. You know that the set score of 1.96 basically will lead you to that value that basically corresponds with your population distribution. The lower tail and upper tail, this is essentially what we're quantifying. This comes from the normal probability table, which I've provided you to with. So you have this on your module. And you will find always the percentage that is below a certain point. If you actually want to transform this and you want to know the area under the curve above a certain point, so that probability above a point, or that fraction of the population, if used on a population distribution, you just have to calculate 1, which is the whole area, minus the actual part below, found below. So that's the percentage found on the distribution table, and you subtract that from the entire area under the curve of 100%. So we talked about the normal distribution table. So you find values that are greater. These are important set values. So here you see the 1.96, which is for the 95% confidence interval. So that's 1.96 corresponds with 2.5. Since we're assuming symmetric situations in a normal distribution, basically it's 2.5% on the negative end, and on the positive end, that means we're looking at plus 1.96 and minus 1.96, which adds up to 5%. If you are interested in a 10%, in a 10% confidence interval, you would basically look for 1.645, but more about that when we talk about normal distribution. The norm dist function essentially allows you to bring this into practice. We will not discuss it in detail. We could if we had more time, but it's basically just following and employing the same principle. What is also important, if you want to know actually what is contained between two boundaries. So let's say we have any random variable. So we have a 65 mean, and we are interested now into values that are within 1.43 standard deviations. So 1.43 standard deviation will translate into essentially 0.9236%, which would be found here, which corresponds essentially then with 7.6% greater than this set score. Since it's symmetric, this will show you the same tail to the left here, and essentially allows for you to quantify what is found in between. So only the blue area can be calculated, by just calculating this part and then employing the principle of symmetry and deducting also the second tail from the same value, which basically gives you only what is located in between those two boundaries. So it's basically utilizing the symmetry of things and allows you to be fast in your calculation. But I think we don't need to go into too much detail. You can also calculate this back. This is the 95% confidence interval, which we can talk about in much more detail. So now, yeah, this is where it's becoming interesting. So this is how you translate this into probabilities. It's basically, it follows the same principle. And you can basically employ these principles for basically your sampling distribution is 100%, and you can employ the set score now to quantify and indicate the probabilities. When it comes to a binomial distribution, you can basically use this for repeated independent events. And so it's a little bit shifting gears from the normal distribution. So you have binary categorical variables. You have trials where you're picking one individual from your population, and you can basically quantify the probability that a certain number of them will have a certain condition met. So the problem here becomes that you have two possible outcomes. Each of your trials will have the same probability. So you have the same probability of success. So if you define success and failure as the individual being diabetic or being not diabetic, the probability of success, let's assume again this prevalence of 10%, the probability of success is always 10% for success. So if all of your trials, the n number of trials are independent, you will actually have to replicate the same calculation, and this is why this calculation becomes factorial. And we'll see how to do this simpler by basically looking at a normal approximation. So when you look into success out of trials, so you have here, you sample 20 individuals, you have a probability of 0.5. You basically see a certain kind of distribution that will basically represent your probabilities to have a certain outcome represented in your sample. And this follows again a normal distribution, and this normal distribution can actually be approximated using a normal distribution. So where is this now? Yeah, so this is the normal approximation. So you have a mean that you assume to be consistent with the number of your trials multiplied by the prevalence in the population. So if you sample 1,000 individuals from a population with a prevalence of diabetes of 10%, you assume that approximately 10 individuals, 10%, 0.1, okay. The prevalence of diabetes is here less than the example that I usually use. So it's 0.1%. So then it's 10 individuals will have diabetes. So the mean is here mu equals n multiplied by the probability of success. And you can utilize standard normal approximation to actually also quantify a standard deviation. And that standard deviation is essentially the standard deviation around these estimates from your sample. And then you can utilize this essentially to use this for hypothesis testing. Good. So this was the theory of today. So the probability distributions I just skimmed through to keep this rather short because it's very specific, but I think we will only use it now in practice. So are there any questions on what we discussed? I know it was quite a bit, and we're actually quite advanced already in terms of time. Are there any questions at this point? If not, then we can quickly turn to our practice lab today, and this is quite fun. So please download the R file for today's class and open it in R. So we essentially we're looking now at again cleaning the environment as the first step. Then we are loading three very particularly dplyr is a very powerful package. I highly recommend to acquaint yourself with this package. Also Dubai is a very useful function, and I will show you in a second why. So library bloodtricks we already installed. In case you don't have any of these installed, please make sure to install them. So dplyr, I believe, will need to be installed. So you click on packages on the right lower quadrant. You can then install here dplyr. The same with Dubai. Dubai is basically a very useful package that allows for you to, how should I say, summarize and employ functions specifically for various strata. And you will see what I mean with that in a second. So make sure that all of these three packages are installed and load them all three. For Dubai, this should take a little longer. Then go on line 9. On line 9, you will basically download the aims data. And you can then with line 10 with load aims, you're basically loading the aims data set. And if you inspect this data set a bit more, you will basically see that there are a lot of various parameters in there. So we have here a certain order number, we have a PID, which is like house number. Then we have various aspects of these houses in Ames, Iowa. We have conditions, we have building types, family home and townhouse. We have house style, we have the overall quality, we have roof style, we have all various variables for these houses. We will also need to load the CDC dataset for reasons that I will show you later. And now we can with ls. You remember ls, if we do ls and just an empty parentheses, we basically see whatever is currently contained in our environment. If we specifically look for ls aims, we're basically getting an overview of all the variables that are contained in the aims dataset. We can now first, so our focus will be on the living room, the greater living room area. We can basically depict this now quickly as a histogram. So we basically will see now the distribution of our living area. We can summarize it. We're basically seeing that mean and median are kind of close to each other. So there's a somewhat normal distribution. We can quantify the standard deviation. And now we're basically getting to that point where we are going back to sampling. So the sample request essentially is here shown as follows. So if we go on question mark and sample, we see now the help for sample. So we have here as the first, as our x, we're entering a vector, which our vector is here aims greater living area. that's the vector. We have then an n, which is our positive numbers. That's basically the number of items to choose from. So we're picking here a sample of 60, and we are not replacing these. That means that it's not a sampling with replacement. So if we do a sample from 1 to 10 and we're picking 5, we're basically getting here 5 entries out of 1 to 10. So 1 to 10, that's our vector. So that's basically a vector from 1 to 10. We're picking out of this 5 with replacement 4s. This will basically get us this list. So you see there are no there's no replacement. So replacement is virtually like putting them back in the pool. So if we do this replacement true, then you see you have here double entries. So if we're doing the same exercise now with aims. So again, let's keep in mind our summary for the overall aims data. So we're building now the first sample of our aims data set. So we're building a sample of 60, and this becomes DF1. So now we're seeing here that's 60 randomly drawn living room areas. We're building this as a histogram, and we're seeing not a very pretty distribution. But if we look at the mean, it's somewhat still resembling that actual mean. So if we do now the same exercise with a second data set, we get a different distribution now. So again, it was randomly sampled with no replacement. 60 entries were randomly chosen. We get a histogram and we get a summary where the mean is this time higher. And this is just to show you essentially how samples can differ from the actual population mean. So this is, for example, this is a sample that is biased from the actual population mean. If we're doing the same exercise now, DF sample mean 500. I'm not sure I'm understanding this. Please hashtag out number 30. I'm not sure that's a fragment from another code. Okay, so but now what we really want to do, we want to see how does now the sampling translate into the probabilities using the central limit theorem. So for this reason, now I understand what this is coming from. Okay, hashtag out, please, lines 30 and line 31. Okay, let's assume we want to repeat this now for 500 iterations. So this is basically assigned here to the object iterations. So we're creating a new object that just contains the number 500. So now we want to build a data frame, which we call DF. So DF is basically 500 observations over 2 variables. We have here sample ID 1 to 500, and we have the sample means are just missing values. So these are NA values. So now what we want to do now is we want to do a so-called iterative loop. So an iterative loop, and we talked about this already principally and in principle. So if you do an iterative loop, it's basically nothing else but telling R to repeat the same process as often as I tell you to do it. So for I, so I becomes here in this context nothing else but a counter. It counts basically from 1. So the starting value is here before the actual column. So you have 1 column length of sample ID. So length of sample ID is just the length of sample ID as a vector. So sample ID per se, oops. So sample ID is this vector from 1 to 500. So the length of sample ID is 500 because length of sample ID is 500. Basically, it's just the length of this vector. And now we're saying for I in 1 to 500, repeat the following. dfi2 is the second column. So if we do head df, head, with head you always get the first 6 entries. So you see here sample ID. This is this vector from 1 to 500, where sample mean is basically an NA entry that goes from 1 to 500. So it's 500 missing values. If I say now dfi2, 2, remember, I indicates here in that regard the row, whereas the 2 indicates the actual column. So the row will basically count now following the value that is being assigned to I. So if you go with I from 1 to 500, it will repeat the same process 500 times. And with each iteration, it will assign the current value on its way from 1 to 500 to I. So this will essentially be then df1, 2, which is the first row in the second column. So this is this cell. If it does df22, it's basically the second row in the second column. df32 is the 3 row in the second column. And this continues up until I then finally becomes 500. So what we're doing here is we're calculating the mean of our sample. So remember, this is the same sample entry that we did here. If we're calculating a mean, this basically just gets us the mean of the sample that has been newly drawn. So we're repeating here 500 times the same process. We're creating 500 different samples and we're calculating from each sample the mean. So if we are now running lines 35 to 40, we're basically getting 500 observations that all represent one mean of our randomly drawn sample. If we are depicting this now as a histogram, we're basically getting now our first sampling distribution. So this is a sampling distribution that basically is each individual entry is one sample mean. And this is the sampling distribution of our greater living room area based on samples of 60. And if you remember the essential sample, if we go back to this one, is nowhere close to normal distribution. But if we look at this distribution, this actually follows a nice normal distribution. So essentially this feeds into the point that the sampling distribution is basically more likely to be a normal distribution as compared to the actual raw data. But it's now, this would be where you could compare your sampling mean, your X bar, to your population mean. So if we go back to summary aims, greater living area, we have here mean of 1500. And if we do now mean of df2 with 1505. So you see that this mean of means, so this mean of our sampling distribution is actually fairly close to our mean of the greater living area as it was in the population. So I would argue that this is not significantly different. So you're being asked here to repeat the exercise for 5,000 means, and I think this is considerably simple. You just need to increase the iteration. So you basically have to copy line 33 to 41 and just place the code here and increase the operation to 5,000 iterations. Any questions on this? So in the next lines, we are now creating quartiles. So remember from last class, we talked about quartiles. We talked about 0 to 25, 25 to 50, 50 to 75, and 75 and greater up to 100. So these are quartiles. So if we're creating quartiles now of prices, so we know that the sales price is sale price, Ames dollar sale price. So these are the prices for which these houses in Ames sold. And this is what we needed the dplyr package for. With ntile, we can actually create quartiles quite automatically. So if we run line 47 and we're going back to Ames, we can see now, oh no, not Ames, Ames price quartile, Ames price quartile. Oh, we need to go to the end of Ames. So now we have here price quartile. So this is a newly developed variable. We have created this variable now with this part. This is where we defined the new variable. With the smaller sign and the hyphen, we're basically assigning ntile sales price 4. So if we just run this part, we basically just see this as a vector, depicted as a vector. So this is the actually assigned values to the vector of the sales price. And we're packing this into price quartile, then it will basically align it with the respective sales price. So now, and this is a very powerful function. So I mentioned before that you can quantify things with the do-by package by basically giving a characteristic of one variable within certain boundaries of another. So if we are looking now, let's look at practice labs 3. So stratify the overpopulation by price, create an additional variable, and compare the sample means in the most expensive quartiles and the least expensive quartiles to the overpopulation mean. And this is what you can do here. So you basically get with summary by sales price. Summary by is a very powerful function that basically allows for you, oops, not like this, and allows for you to calculate group-wise summary statistics. So you do with summary by, you can quantify in the respective quartiles your function. You create a mean. So summary by sales price, and here the mathematical tilde will basically define that group. So you want to stratify it as per price quartile. So you get sales price as per price quartile from the data Ames, and the function that you're employing is mean. So essentially summary by will basically give you here price quartiles 1 to 4, sale price mean corresponding with the respective price quartile. If you do the same with the greater living area, you can see to what extent the greater living area will basically differ between the prices. So you see the more expensive the greater the living area. You can also quantify a different function, so you can exchange the function mean by the function standard deviation. And you basically see now the standard deviations for the respective quartiles. So you see that the variability is higher with greater numbers, which are also to be expected. And you can also quantify the length, which is the number of entries in each quartile. Since we have 2930, these are reasonable. These are reasonable values at 733. That's 1466. 2300. Yeah. So you basically 94. Yep. So you basically get each 4 equal parts for each of those. So that's AIMS. So the only thing that is to be done by you is the formal comparison here. So draw the conclusions that are being asked for here in practice lab 3. So you basically repeat here some of the aspects. No, we didn't take a random sample of price, so you can also repeat this. So just make sure all of these points are kind of addressed. So it's create a data set that was 500 from the old population. How does this mean? So we have done that. So you're here being asked to create that random sample of 50 from price, best point estimate for those 50 price estimates. Then we have the data frame was 5,000 sample means, and then we have stratification as per the price, which I've shown you how to do. Good. So now there are a few exercises concerning probabilities. So, and these are considerably simple. So if you have a probability of rolling a 6 on a die, so this is simple, right? You know that the probability of such a 6 to occur is 1/6. So you basically have 6 possibilities. So it's a success over trials. So you have out of 6 different possibilities, you have 1 possibility to have a success. So this, as a consequence, is 1/6. If you roll the same die 3 consecutive times, you're basically looking at the same probability for each time. So the probability is actually, that's the one. So the probability is actually, again, 3 times 1/6. The way you would approach this is essentially 1/6. So 1/6, that's 16.66%. If you run it a second time, it's again 1/6. So the way you're basically looking at this, since it's 2 mutually exclusive events, it's 1/6 multiplied by 1/6. And if it's third time, it's again 1/6. So this is your probability of essentially rolling 3 times a 6 in a row. If you quantify the probability of rolling a 6 as a 1 and a 6 again, you're essentially looking at the same probability as 1/256, essentially. It's the same probability. Then here you're being asked to define categories of random variables. I would ask you here to be a little creative and think maybe of variables you have in your enhanced data set. Maybe this also kind of gives you some inspiration to familiarize yourself with the data set already. So you basically ask for a continuous variable, a categorical variable, and a discrete variable. So give 2 examples for each group. So I think that should be simple. And then we have, yeah, this is where the CDC data comes into play. Good. So what we can do here, so this is our CDC data set. So let's do question 4 after. So we have a CDC weight in kilograms. So if we inspect CDC, we have here weight in kilograms, which is basically weight in pounds divided by 2.2. So the conversion factor between pounds and kilograms is 2.2. So CDC weight in kilograms is now, so we have this is the distribution in pounds. The distribution of weight in kilograms is basically substantially lower. Then we have height in centimeters, because height is here in inches. So we need to, so 1 centimeter is, oh no, 1 inch is 2.5 centimeters. So we're converting it in the same fashion. The reason why we're doing that is because BMI follows the calculation of weight in kilograms divided by height in meters squared. So we have height in meters is now calculated the CDC height in centimeters divided by 100. So 1 meter contains 100 centimeters. And we're ending up with CDC BMI in line 75. That basically allows us now to kind of quantify BMI. So remember, I think we talked about it last time, that BMI is basically categorized, and it's not arbitrary, it's basically defined categories that are defined by the WHO. Everything smaller than 18.5 is considered malnourished or undernourished. 18.5 to 25 is considered normal. 25 to 30 is considered overweight. Greater than 30 is considered obese. Up until 35, everything greater than 35, I forget, it's very obese, so to say. And since you see here quite large numbers, we have here some outliers that are basically definitely qualifying as very obese. Then in line 78, we're basically assigning CDC to DF, which we're overriding our AIMS data now. And now we're calculating the index points. So index points are essentially those set equals 1, set equals 2, set equals 3. So either it's -3 or it's +3. So it's considerably simple how to calculate this. So if we are calculating mean DFBMI -1 multiplied by SD DFBMI, we're basically getting the lower index point for 1 standard deviation. If we calculate +1 multiplied by standard deviation BMI, we get the positive. So this essentially what I have done here is I'm just concatenating it with C. So your output is basically this. You can make this aesthetically more appealing. You could hypothetically, you could round it. So I leave that to you to kind of make this aesthetically more appealing. You could, with the round function, you could hypothetically, you can round it to do decimals. It's actually nicer to do that. I would encourage you to do that. So now we have a rounded overview. So same, so if we are now, so we have a mean of BMI of, what did that, summary DF BMI. So we have here mean of 27.22. We have now 21.8 to 32.6 contains 68% of all the data. We have 16.4 to 38 contains 95% of all the data, and 11 to 43.4 contains 99.7 of all the data. Why is that now interesting? Because you can utilize this to essentially also use various ways to depict your data. If you use the same formula and you add here airline. Airline is basically a command how you can make a vertical line. So if you say v equals 30 or 40, it makes you a vertical line exactly at 40. So this is just another way to kind of show this nicer. So we're using here a color red and line type equals 2. Line type equals 2 is essentially a dashed line. Line type 1 is the solid line. Color is self-explaining, I assume. So we have this airline. We can now find exactly that vertical point that is consistent with our first index point. So that's our 21.8. So if we say airline, let's redo the histogram. If we say airline v equals our first index point in red with a dashed line, we're getting exactly this. Now this is the second index point. This is the third index point. We can do this again with 89, 90, and 91. Gives us again these 3 different index points. So now we have quantified. So we have between the red ones, we have 68%. Between the green ones, we have 95%. Between the blue ones, we have our 99.7%. Then we have p-norm. P-norm is a way how you can quantify now this normal distribution function. You remember when we model out the distribution function, the normal distribution is nothing else but an arithmetic function. It's a mathematical function. This mathematical function can be integrated and thereby you can quantify the area under the curve. So you know exactly what fraction of your, if you remember this depiction, we can, I don't know, it was the, so we can quantify what in here is basically here light blue, what's dark blue, oh no, slightly darker blue, and here we have the dark blue. So we can quantify this by assuming this is a mathematical function, and this is what the p-norm function does. So p-norm basically quantifies this, and you can then, with the p-norm function, you give in p-norm, you quantify the actual index point, that's your x. So if we go on p-norm, p-norm, you quantify our q, the labeling is q, you give it a mean, you give it a standard deviation, and then it will basically quantify this for you. So we know now that p-norm for +1 to -1 will basically contain 68% of your population. If we're doing the same exercise, now it's 95.44 or 45. This is within 2 standard deviations, and now we have 99.7 for 3 standard deviations. So it's bringing to the test those index points that we have discussed before. So that's just basically practicing what we've discussed before. Then there are, lastly, from 99 to 107, you basically have different tests that are being used to actually quantify whether distribution is a normal distribution or not. I'm just showing you these for the sake of completeness. They're not very commonly done, to be honest, but you can utilize them for smaller data sets. This is sometimes relevant. So with Shapiro test, actually too much data for him. So Shapiro test would be DFM BMI. If we just say, okay, we want 1 to 4,900, it basically gives you a Shapiro-Wilk normality test. It shows here that the p-value is smaller than 5%. That would indicate it is actually not normally distributed, but this is a question of the sample size. So if we take a smaller sample, let's just do 40. So here we get borderline is significant. If we do 10, so now we actually we're not having a significant test. So library node test is the Lilly test. Is another test to basically test this. This is the Lilly force as a variant of the Kolmogorov-Smirnov test, which is here on 107. If we do this in a smaller sample, we're also getting here a non-significant test. So as soon as you have a large sample, these tests are always positive and they will always turn out significant because things just lose their shape. If you have KS, also here, the Kolmogorov-Smirnov is significant. So these are just the functions that you will need in case you want to formally test your normal distributions, which I don't think is often necessary. It's sometimes necessary, but not often. In most cases, you have sample sizes that are exceeding these thresholds of 30, which most statisticians will agree to as a threshold beyond which you can assume it's normally distributed. So this is now the last example. That's question 4. These are just those values, how you can basically, those formulas that you basically can use to calculate the examples that are listed here. So we're doing here the same exercise as shown here with, no. Where is it? So we have here, what is the probability that if you randomly select 4 individuals from this population, that at least one of them will be diabetic? At least one basically indicates here 1 minus p, that there's none. So you quantify, you remember that the probability needs to add up to 100%. So if you know the probability of no individual being diabetic, you can quantify 100 minus that probability of no individual being diabetics. And this is basically what you do here with the first exercise. So you have here, oh, wrong, this is actually it's at most 3. Okay, so we have 4 individuals. So this is exactly 3. Exactly 3. Okay. So 4 individuals enter a clinic. What's the probability that exactly 3 are diabetic? So this is done with the d-binom function. So with d-binom, you basically get the exact quantification of the probability of an individual being diabetic or part of the success group. So if you are interested in exactly 3 in a sample size of 4 with a probability of the population of 0.1, you get with d-binom, you get exactly 3 are diabetic. If you're now in the next example, so that probability is now (0.0036). You have 12 individuals entering barber's office and a hair salon. exactly 4 have alopecia, which is hair loss. So 12 individuals enter a hair salon. So the size equals 12. What's the probability that exactly 4 have alopecia with a prevalence of 20%? So it's 4, the sample size is 12, the prevalence is 0.2. So your probability here would be 0.13. If you have 15 individuals in the dentist office, what's the P that exactly 3 have a dental cavity with a prevalence of 30% in the population? Exactly 3. So it's basically, it's the same example, but the test. So we have 3 individuals, exactly 3 have dental cavity. So 15 individuals, 3 have a dental cavity, and you have a prevalence of 30%. So the probability here would be 0.17. And lastly, and this is a little bit more challenging one. So we have 15 individuals, and we have at least 3. So what does that mean, at least? If there are 15 individuals, if we have at least 3, that would mean we need exactly 0. That means that none have basically a dental cavity. We have those where at least 1 has a dental cavity. So it's a quantification of risk of different samples, right? So hypothetical samples. So we have that sample that none have a dental cavity. We have those where exactly 1 has a dental cavity, and then we have 2, and then we have 3. So essentially, if you are now quantifying this as a whole, we have 0.3%. Oh no, 30% probability, 0.3. This is 30% probability that at least 3 have a dental cavity. So it's the scenario for no individual having dental cavity, 1 individual having dental cavity, 2 individual having dental cavity, and 3 individual having dental cavity. So if you do not want to quantify it in that way, you can use the normal approximation by basically saying 3, 15, and 30, and you do a normal approximation of your result. And that gives you again those 30%. So that's how you approach these examples in the practice lab. Okay. Were you able to follow this, the coding? Are there any questions on the coding? Are you going to be okay with practice labs 3? Is this going to be solvable? So again, keep in mind, so the things that are really for you to solve are basically the random sample from price, the repetition of the exercise with 5,000 sample means rather than the 500 that we have used here with the greater living area, and to kind of familiarize yourself with the functions. So this is really the ask for this practice lab. Any questions from anybody? If not, that we can conclude for today, and I'll see you again next week in person.